Welcome to this first of the GCSE Physics webinar series for 2019 at Invisible College. And this one's going to be on the subject of electricity, and this should cover the content for all exam boards, for all specifications. And again, we're going to start for the first hour in teaching the topic. Now again, once again, just to remind you, those of you in attendance, please do type the questions into the Q&A box, not the chat box, and I will address those questions towards the end of the webinar. The first hour is going to be teaching through the topic and the ideas of the topic, and then the second hour I will devote to answering the exam questions that you all received in your exam questions pack. So let's get started then on the subject of electricity. So to start with, the first topic that we're going to cover is the idea of charge, because it is fundamental and it is one of those topics that you all voted for the most. So let's get started with that. So all of this requires you to understand a little bit about the structure of atoms. Now, charge is a fundamental property of matter in general. It's like mass in that respect. Matter in general is mass, and mass is made of atoms. Now, atoms are made up of subatomic particles, each of which have either a positive charge, a negative charge, or no charge at all, or are neutral. Now, again, the idea of charge can be a little bit of a slippery one for some students, but it is essentially a fundamental property of all matter. Now, the thing that gives an object a charge is the balance between the total number of negatively charged electrons and the total number of positively charged protons in all of the atoms that make up that objects. Now, atoms are electrically neutral overall because they contain an equal number of electrons and protons. In other words, they contain an equal number of positive and negative charges. But if that changes, if the object loses electrons or gains electrons, then the object can become either positively charged overall or negatively charged overall, respectively. So, in order to understand electrostatics, in other words, the ideas concerning electricity, where we're just thinking about charge on objects rather than charge moving through objects, which is electric current, you need to know about the basic structure of the atom. So to remind you, we have three subatomic particles, and the particles are arranged in this manner. We have the electrons orbiting the nucleus at these concentric energy levels, and we have the protons and the neutrons in the nucleus, in the central portion of the atom. Now again, this model, as being depicted here by this animation, is somewhat limited because the nucleus is not drawn to scale. The electrons are drawn as particles orbiting the nucleus. Later on in your studies of physics, you'll realize that there are other models of electrons where you can consider them to be standing waves around the nucleus at these locations, which represent different energy levels. The lowest energy level in the nucleus, nearest the nucleus, and the highest energy level furthest away from the nucleus. Also, this model is, again, somewhat flawed in the sense that it depicts an atom as being a two-dimensional object. Of course, atoms are three-dimensional objects, so perhaps the model could better be represented in this manner here. Let me just change the audio here so I don't deafen myself every time I click a button on the PowerPoint here. There we go. Sorry about that. All right, so all materials, all matter is fundamentally made up of atoms. Now, again, this is somewhat of a simplification, but it is a very good generalization. All matter is made up of atoms, and all atoms are composed of these three types of subatomic particles, with the protons and the neutrons found in the nucleus, in the central portion of the atom. So, to remind you, protons carry a positive electrical charge, neutrons do not carry any overall charge, they're referred to as being neutral, and electrons carry a negative charge orbiting the nucleus of the atom. And the atom itself overall has a neutral charge, neither positive nor negative overall, because the positive charges on the protons are exactly equal in size in total to the negative charges on the electrons, because again, an uncombined, unbonded atom is an object which always has a equal number of positively charged protons and negatively charged electrons. But if an atom loses an electron, what this means is you have one more proton overall than you have electrons in the atom, and therefore you have one more positive charge than you have negative charges. And so the atom no longer is referred to as an atom, it's referred to as an ion, specifically a positively charged ion. Now, in contrast, if an atom gains an electron, it becomes a negatively charged ion, because in this case, the number of negative charges outweighs the number of positive charges by 1. Now, another thing that I want to stress here is that when we measure the amount of positive or negative charge on a proton or an electron, we're not measuring it in standard units. The standard unit of charge is the coulomb, but for the purposes of discussing atoms and subatomic particles, the amount of charge on an electron or a proton is effectively the same amount, but it's a tiny fraction of a coulomb. It's about 1.6 times 10 to the power minus 19 of a coulomb. Now, this is the smallest possible charge that can exist on any object. And so, because it's a very small number and it can only be represented in powers of 10, for convenience, we say that the proton has one atomic unit of charge, positive charge, and the electron has one negative unit of charge. So, this is the basis of understanding electrical currents. But before we go on to that, one of the topics that you all wanted me to go over here is the idea of charge and electric fields. Now, we're going to be looking at that in a little bit more detail here, but in order to illustrate that for you, I'm just going to use one of these very handy simulations that we get from the PHET, P-H-E-T website here. So if ever you want to find some simulations to use in your revision, I would thoroughly recommend typing in PHET and then the word simulations into Google, and this will take you to the website, which is run by the University of Boulder, Colorado, which has produced these very useful animations. So here, if we have, let's just say, a space with no electric field in it, and we place 1 nanocoulomb, 1 billionth of a coulomb of positive charge, here we see that this charge creates an electric field around itself. Now, this is represented by arrows pointing away from the positive charge. A field, an electric field, a gravitational field, a magnetic field, the word field in physics simply means a vector quantity which changes at all positions in space around the object causing that field. So in this case, the field lines represent the strength of a force exerted on a positive charge. So if we imagine this sensor over here is a positively charged object, wherever I place this object in this field around this object which is causing the field, it will experience a force which will repel it away from this positive charge. So by convention, the field lines around a charged object represent the direction of the force exerted on a positively charged object wherever you happen to place it. So if I place it at a relatively large distance away from the object causing the field, the force, which is represented by this yellow arrow here, is relatively small. If I move it towards the positively charged object, that force increases in magnitude. And so we can say that the strength of an electric field, which we can measure in terms of volts, and we'll talk about volts in a little while, we can see here that the strength of that electric field increases the closer you get to the object which is causing that field, and decreases the further away from the object causing that field that we go. Now, the other consequence of this idea of fields is that if this is the object causing the field, then if I place this sensor and measure the voltage, the work done per unit of charge at a particular position, then if I placed this sensor at the same distance but at a different position away from this object, so equidistant in a circle around this object, we would find a line which represents all the positions where the force acting on a positively charged object would be the same. So this is called an equipotential line. So if I was to place this sensor over here, it would have the same force acting on it, the same repulsive force. Remember, the sensor represents a positively charged object. It would have the same repulsive force acting on it as if I was to place it over here. The only difference would be the direction that the force is acting on it. And so these are called equipotential lines. And so again, if I put the sensor at this position, it would have this much force. Again, forces are indicated by vector arrows, where the direction of the arrow indicates the direction of the force, and the size of the arrow indicates the magnitude of the force or the strength of the force. So if I was to place this sensor at a different position, but at the same distance from the object causing the field, we would find that the same strength of forces acting upon it, but in a different direction. So in this way, we can define the field as a vector quantity which changes at all places, at all positions around the object causing the field. It changes either in terms of the magnitude, or it changes in terms of the magnitude and the direction, or just in the direction. So an electric field is a vector quantity which changes in magnitude and or direction at all positions around an object with a charge. So that's for a positive charge, and you'll notice again, by convention, by agreement, physicists will draw the field lines, the flux lines as they're called, which are normally drawn as straight lines with arrows on them. In this particular simulation, they're being drawn as individual arrows, and the brightness of the arrows indicates the intensity of the field at these positions. The directions obviously indicate the direction of the field. But by convention, the arrows will indicate the direction that a force will be exerted on a positively charged object by that field. So if we reset this and change that charged object to a negatively charged object with the same amount of charge on it, but negative charge. So in this case, we have a negatively charged object with a charge of -1 nanocoulombs, 1/1000th of a coulomb of negative charge. Here we can see that the field lines are pointing towards the object, and the reason for this is that a negative charge will attract a positively charged object. And so here again we can see that at all positions around the object causing the field, the strength and or the direction of the force experienced by a test positive charge will be indicated by these field lines. So charge is a fundamental property of all matter, all objects. Either they have an overall positive charge or an overall negative charge, and the reason they have an overall positive or overall negative or are neutral is because of the number of units of negative charge within them carried by electrons and the number of units of positive charge within them carried by protons. So if we now put a negative charge in this same field over here, we can see that the field lines or the shape of the electric field in this whole region changes. So this is part of the reason that negative charges will repel negative charges. It's because the field lines basically push against each other in this manner. If we change the negative charge to a positive charge over here, the field lines connect the two objects, and so the negative charge and the positive charge are attracted to each other. And in this case, if we change the negative charge to a positive charge, again, we see that the field lines go in this direction. They push against each other. Now, you should be able to draw simplified diagrams of the field lines of around charged objects in this manner, and also should be able to identify what the charges are on two objects from the shapes of the field lines if those are drawn for you. So again, I would encourage you to have a play with this simulation. It is very good. It gives you a very good understanding of what we mean by, or the shapes of fields, and also the intensities of those fields around positive and negatively charged objects. Okay, so that's what charge is. Charge is a property of all materials, but what we're talking about so far is electrostatics, static electricity. The word electricity is a very general, very vague word. Physicists will talk about static charge, or they will talk about electric current. So a static charge is a net positive or net negative charge on an object. But that charge, if it's a static charge, isn't going anywhere. Once that charge flows to another object or through a material, then we have a flow of charge in one average direction. And this is what we call an electric current. An electric current is the flow of electric charge, usually carried by electrons, through a material. Now, most of the examples that you'll come across in GCSE Physics will be the flow of electrons through conductors in a circuit. So in certain circumstances, there can be a buildup of electric charge which is not free to move. And again, this is called static electricity. An excess of electrons, in other words, having more electrons in an object than protons, causes a net negative static charge to be on that object. And again, a shortage of electrons, in other words, more protons than electrons, causes the opposite. It creates a static positive charge on that object. Now, where static electricity continues to build up in one place, it can result in a spark or an electric shock when those electrons eventually move from the object where they are in excess to some other object where there are fewer of them. Now, the important thing to stress here is that it's the electrons which will move. Protons are locked up in the nuclei of atoms. When static charges discharge and produce an electric current like a spark, it's the electrons which are moving. Protons do play an important role in electrostatics because they provide the positive charges within atoms and within matter. But the protons are tightly bound within those nuclei and they're not free to move around. So this is a simulation of the ions, the positively charged ions in a metallic conductor, and these are the outer shell electrons which have been shared by each one of these metal ions. Each one of these metal ions was a metal atom which shared its electrons. Now, when there's no current flowing, those outer shell electrons are evenly shared between all of these atoms. But because each of these atoms has donated its outer shell electrons to the so-called sea of delocalized electrons, this leaves behind positively charged metal ions, and the negatively charged electrons are free to move between those positively charged ions. So this is the situation in a metallic conductor when there is no electric current flowing. An electric current is the average movement of charge, in this case negative charge, from one part of a conductor in one average direction to another part of a conductor. So when the current is switched in a circuit, all of the conducting elements in that circuit, the wires, the devices, will have electrons flowing through them in one average direction. So the flow of electrons around the circuit is called the electric current. The size of the current depends on the number of electrons passing each fixed point in the circuit per second. Now, in contrast, in an insulator such as plastics, electric charge can't flow because the electrons are all tightly held onto the atoms. They're not free to move around. They're not delocalized the way that they are in metallic conductors, for example. So insulators are useful in electric circuits because they stop the flow of current. So an example of this is the plastic insulation that you find around metallic wires in a circuit. But in some situations, insulators can develop a static electrical charge. So here's one such example. When two insulators, such as wool and plastic, are rubbed together, some electrons from the atoms on the surface of one insulator are transferred to the surface of the other. So this produces a static electrical charge, and this process is called charging by friction. So we start with two objects, two insulators, two objects made of insulating materials which do not have delocalized electrons which are free to move through them. So we have wool and we have polythene. Now, when these two are rubbed against each other, the friction transfers electrons from one object to another. Now, if these objects are composed of atoms, and again, within each of these objects to start with, you have an equal number of protons and electrons. This means that once the electrons are transferred from one to the other, each one of those objects either has an excess of electrons, in other words, it has more electrons than it has protons, or it is deficient in electrons. In other words, it has fewer electrons than it has protons. So friction will move electrons from the wool, in this case, to the polythene. And so the polythene gains a net negative charge because now it has more negatively charged electrons than it has positively charged protons. And in contrast, the wool has lost electrons, and so now it has a net positive charge. It has more positively charged protons than it has negatively charged electrons. So electrons static charges can also produce other effects, which many of which you've probably experienced for yourselves. So electrons in hair, for example, if you rub hair onto a balloon, the electrons in hair can be transferred onto the balloon. And so the balloon becomes negatively charged, and this leaves the hair positively charged. And this is why the hair can then appear to stick to the balloon, because, of course, positively charged objects are attracted by negatively charged objects. Another common thing that you may have seen is the Van de Graaff generator. So Van de Graaff generators can be used to charge other objects or to produce sparks, some of which can be quite dramatic. So if we run this Van de Graaff generator, what's happening is the metallic brushes, which are connected to the dome, are stripping electrons from the rubber belt and allowing those electrons to build up on the surface of the dome until eventually the static charge is so high, it is able to break through the insulating air barrier between the surface of the dome and this earthed metal dome over here, and this produces a static or a spark. That spark then jumps across the gap, carrying the electrons to this dome over here, and then those electrons flow down to Earth. So, lots of different types of Van de Graaff generators. They all work in different ways. The model that you saw working here works in the following way. Now, I'm explaining this just because it is something that often comes up in exam questions, even though it is not specifically referred to in many specifications, but also it's because one of the questions that many of the students voted as being one of the more challenging ones in the exam questions pack that they received for this webinar concerns Van de Graaff generators. So, as the belt, the rubber belt in the Van de Graaff generator turns, electrons are picked up from the metal comb, the metal brushes. The right-hand side of the belt that's rising becomes negatively charged as it carries the electrons upwards. Now, inside the dome at the top, the electrons are taken from the belt by the brush and then pass onto the surface of that dome. Eventually, those electrons build up, and so you have a build-up of a static negative charge on the surface of the dome. So the dome gradually becomes more negatively charged, and the side of the belt coming down from the brushes over here becomes increasingly positively charged because, of course, it's given up its electrons to the dome. So as the positively charged side of the belt comes downwards, it regains electrons, and then the process of carrying electrons back up to the top can continue, making the dome increasingly negatively charged. So once a high enough charge is built up in the dome, it discharges itself across to the earthed dome nearby as a spark. And so the spark is actually the light being given off as the electrons flow through the air and ionize the gas particles in the air. So we mentioned that there are forces between charged objects. So if we have a look here, we see that we have two charged objects, these polythene rods, which have been rubbed to gain positive charges. So if we imagine that the rod in the cradle has a positive charge and the rod in the hand has a negative charge, let's have a look at what happens here. So we would imagine that these two would attract each other because, again, imagine the field lines connecting these two, and of course they do. If we now have a look at what happens when we have the same charge, a like charge on both, they would repel each other. Now, again, this is a fairly common practical that you may have seen, a practical demonstration. So, again, positively charged objects and negatively charged objects tend to attract each other. If we have two positively charged objects, they would tend to repel. And similarly, if we have two negatively charged objects, they would also have a repulsive force between them. And so we can conclude here, and again, the reason for this goes back to that simulation that I showed you. It's the lines of force or lines of flux which are pushing against each other in the case of like charges, or pulling towards each other in the case of dissimilar charges, positive versus negative. So two objects carrying opposite electric charges are attracted to each other, while two objects carrying the same electric charge will repel each other. So why do electrostatic forces attract or repel? Well, again, the idea here is that a charged object creates an electrostatic field around it. The electrostatic field affects the space around the charge in a similar way that the gravitational field affects the space around an object with mass, or a magnetic field affects the space around a magnetic object. So when a charged object enters one of these electrostatic fields, the object experiences a force, and the force is either attractive or repulsive. Now, again, this goes back to what we were talking about with this simulation here. By convention, whenever you draw the field lines around an object, you would show them emanating outwards from a positive charge, or you would show them going towards a negative charge. Now, the reason for this is because by convention, by agreement, the direction of the field lines on a electric field diagram indicate the force experienced by a test positive charge placed somewhere within that field. So if the test charge is always positive by convention, then if you place that into an electric field around a positive object, it will always be a repulsive force. If you place that into a field around a negative object, it will always be an attractive force. So, another idea that many of you voted for me to go over is the idea of electrostatic induction. So when charged objects move near to uncharged objects, a charge can be induced on the uncharged object. Now, the word induced simply means caused or caused to happen. So if we take this example here, again, somebody rubs their hair against a balloon. The balloon gains a net negative static charge because electrons are transferred to the balloon. But if you then place that balloon somewhere near a wall, the wall begins with a neutral charge. It has exactly the same number of protons and electrons in it. But what ends up happening is when you place this near the wall, the negative charge on this object repels the electrons in the near surface of the wall and causes those electrons to move away from that surface. This leaves behind a region of positive charge on the wall, which of course then attracts the negatively charged surface of the balloon and causes a attractive force, causing the balloon to stick to the wall. So this is electrostatic induction. This is the induction, the causing of a static charge to appear on an uncharged object by bringing a charged object near to that uncharged object. So induction means to influence or to cause without contact. So after the charge has been induced in the wall, the balloon and the surface of the wall have opposite charges. They attract each other, and then this causes the balloon to stick to the wall and not fall off the wall. So I'm sure this is something that many of you have seen. We've mentioned also some other interesting phenomena, so how and why combing or brushing hair can cause it to stand on end, particularly if it's long hair, like this rather cute but unfortunate looking and confused looking dog over here. You can see that it's had its hair brushed, and because it's quite long hair, clearly somebody has brushed its hair with a insulating object such as a plastic comb. The hairs have become charged, but all the hairs have an equal charge, a similar charge, and repel each other, causing them to stand on end. So you may have experienced at some point, in fact, most of you probably have experienced at some point, the shocks and sparks that can occur because of a static charge buildup on your body. So you may have been walking around and reached towards a door handle or something like that, and then gotten a small electrical shock from that surface. You may have even seen the spark if the room happens to be quite dark. So the reason behind that is, again, because you have a static charge buildup on the surface of your body. Either you've been wearing, for example, polyester or artificial fibers on various parts of your clothing that have been rubbing against each other for some time, causing a static charge buildup, and you've not been earthed because you've been wearing rubber-soled shoes, and then you walk along with this static charge buildup on the surface of your body, which you're not aware of, and move over to a grounded object, such as a radiator board, you touch it, and a spark jumps across that gap. So, many of these effects, such as, for example, why monitors and TVs tend to get covered with dust, are due to these electrostatic phenomena. So how and why a TV screen can attract your hair as well is a similar thing. And also lightning is another one of these effects of electrostatics. This is an electrostatic discharge, and this is caused by clouds moving past each other, causing a buildup of negative charge in the lower portion of a thundercloud, and this then induces a positive charge on tall trees and buildings, which can then cause a massive discharge of electric current in electrons to flow from the net negative charge on the underside of the clouds to the induced positive charge on the upper surfaces of tall buildings and trees. So eventually, once this static charge has been built up, the electrons jump across that gap to the Earth, and the burst of electric current that occurs in the air is referred to as lightning. So combing hair with a plastic comb can sometimes produce a static charge, and this can then be used to induce a positive charge on a nearby uncharged object, such as bits of paper, which can then be attracted enough to lift those bits of paper onto the comb. So if you comb your hair with a plastic comb, typically made of things like polythene, the comb will pull some of the electrons off the hair, and this then causes the comb to gain a net negative charge. But if you then hold this charged comb over some small pieces of paper, a positive charge is induced on the top surface of the paper. And again, this can then cause a attractive force to occur between the oppositely charged objects, which then attracts them together, causing the pieces of paper to move upwards and adhere to the surface of the comb here. Now, will this work with a metal comb is the question that I'd like to ask. No. So if you can see the question pop up on your screen, just go ahead and click yes or no. If you can't see the question pop up on your screen, then just go ahead and type Y or N in the chat so I can see what your responses are. I'll pause there for a second and let you answer that question. So what do you think? Yes or no? Will that same experiment work with a metal comb? Okay, so I'm going to stop the polling here. So it seems like about 62% of you have said no, and the remainder have said yes. Okay, good. Yeah, so for those of you who said no, you are right. The reason why this would not happen, again, static charges, charging by friction, as we saw in the previous examples, this occurs when you have insulating objects rubbing against each other. If you have a metal comb, then this will not work. Metal is a conductor, and so any static buildup on the surface of the comb is immediately shared equally through the body of the comb. So the metal comb would also easily pass its charge onto the person causing it, and the person holding it would be acting as an earth for that charge. So for these two reasons, metal objects cannot be charged by friction, although they can be charged by induction. So I'm just going to skip past this just to, because it's the same kind of explanation here. So another thing that you may have seen is a rather interesting phenomenon is the behavior of water, streams of water, when you place them near a charged object. So let's imagine somebody takes a plastic comb, an insulating comb, and combs their hair with it. So again, as we saw before, the comb becomes negatively charged. If you then place that comb next to a thin stream of running water, you'll find that that stream of running water should be attracted towards that comb, sometimes quite dramatically. Now, the reason for this is because water is a polar molecule. Water is made up of molecules which, even though they have no net charge overall on them, they tend to have an uneven distribution of charge on the water molecules. So in order to illustrate that, let me just go ahead and flick over to this board over here. So to illustrate that, water is H2O, and water molecules have this interesting V shape, or they are bent-shaped molecules like this. Now, what you have here also is two non-bonding electrons in the outer shell of the oxygen atom, another two over here. These are called lone pairs of electrons. You also have a pair of electrons shared in this covalent bond to this hydrogen, and another pair of electrons shared in this covalent bond to this hydrogen. Now, the overall number of protons and electrons in a water molecule is equal, so the water molecule overall is neutral. However, because you just have a hydrogen nucleus sitting at this end of the water molecule, at either one of these two ends of the water molecule, and because you have this pair of negatively charged non-bonding electrons over this end of the water molecule, this end of the water molecule here is slightly negatively charged. We use the Greek symbol delta to indicate a slight negative charge, and this is in comparison to, or with respect to, this end of the water molecule down here, which conversely has a slight positive charge. And so what ends up happening is that when you take the negatively charged comb and you place it near a vertical stream of water flowing downwards, the positive ends of the water molecules orient themselves towards the negatively charged cone because of the electrostatic field around the negatively charged cone, and will therefore be attracted in this direction to the cone. This causes the stream of water to flow in this direction. And so here we say that water, the molecules that make up water, even though they have no overall charge, these are examples of polar molecules. They have an uneven distribution of internal charge across them, causing this rather interesting behavior that we see here. Okay, so we've already explained this in depth. So negatively charged cone induces a positive charge on the water molecules. Now, this is a bit of a simplification. It's sufficient for GCSE. The actual proper explanation is the one that I've already given you, is the fact that water molecules are polar in nature, and so the positive, the slightly positive ends of the water molecules near the hydrogen atoms will orient themselves towards this side of the stream of water due to the electrostatic field, and that side of the water stream will then be attracted to the negatively charged cone. The water molecules themselves adhere to each other but via a strong type of intermolecular bonds called hydrogen bonds, and therefore, as the water molecules on this side of the stream are pulled towards the negatively charged cone, the other water molecules will follow them. So getting a shock from a carpet, something that probably you've all experienced. So if we imagine we have a metal door handle here, and somebody brings along a negatively charged hand, which has picked up a static charge from the carpet, from the soles of their feet or shoes rubbing against the carpet, we bring the fingertip towards here, and the negatively charged electrons will jump across the gap, and you will experience this as a tiny electric shock. So let's see here. Okay, so the explanation is when you walk over a nylon carpet. Remember, nylon is a insulating material, as is the rubber or material that makes up the soles of your shoes. So the two materials are being charged by friction as your feet move across the carpet. So the electrons are picked up by your body, by the shoes, and then distributed over the surface of your body due to the friction between the soles of your shoes and that insulating nylon carpet. So these electrons then spread out over the whole of your body. The whole of the surface of your body excuse me, takes on a static negative overall charge. So when you approach the metal door handle, the negative charge on your fingers induces a positive charge on the door handle, and then just before you touch the handle, a transfer of electrons takes place from your fingers to the handle. You feel a small shock, which then takes place. So let's have a look now at some of the applications and the hazards of static electricity before we move on to the next topic that you all voted for, which was the idea of electric current and circuits and Ohm's law. So on average, 3 people are killed by lightning each year in the United Kingdom. During 2001, forest fires threatened to destroy houses in the suburbs of Sydney in Australia, and the fires had been started by lightning. So lightning can be incredibly damaging both to individual human beings, but also to large segments of either the urban environment or the natural environment. Now, in July of 2006, a thunderstorm hit an area of Washington in the US, and as one house was struck by lightning, the television exploded, then caused the house to catch fire. And this is actually quite a common event, unfortunately, when houses are struck by lightning, if those houses are not properly protected by the kinds of measures that we'll see shortly. So lightning can cause a surge in the electricity supply, and unprotected equipment which are plugged into the mains of these houses can then be literally burnt out, and then fires can be caused in the home due to that, which can then obviously be incredibly damaging. I actually experienced this myself relatively recently, where a power surge due to a nearby lightning strike completely destroyed all of my computer equipment, causing me to have to replace the whole lot. And that taught me a very valuable lesson: buy an uninterruptible power supply and a very expensive surge protector if you want to save your equipment. So microchips, particularly memory chips, RAM chips in computers and other devices, are very susceptible to these power surges. So tall buildings are at risk of a lightning strike during thunderstorms. So to prevent damage, lightning conductors are fitted to these buildings. And you see one of these being indicated by this magnified section. This cable here that you're seeing down the side of this house, or rather the side of this cathedral, this church, is a lightning conductor, which is connected to the spire here, which is the highest point on the building. So the idea of a lightning conductor is to provide an easy, harmless path for that massive electric current to the ground and preventing it from then passing into the building, causing fires and damage to electrical equipment and so on. So this is how a lightning conductor protects a building. A lightning conductor essentially is a low resistance path for the flow of charge from the lightning strike down into the earth rather than through the whole building. So the distinction here would be like this. So we can see here that the house that was, or rather the building that was protected by the lightning conductor has a much lower damage. It will experience maybe a little bit of damage, but nowhere near as much as the building not protected by the lightning conductor here. Okay, so lightning causes damage to buildings, and the reason for that damage is because of the huge currents involved. Now, I want you to hold on to this idea because later on we're going to be talking about the domestic uses of electricity and electrical safety in the home, but it's the same principle. It's the flow of electric charge. In this case, in the case of lightning, something like 20,000 or more amps, which can heat materials to high temperatures, causing fires, and also loss of structural strength. When high electric currents pass through materials, it reorganizes the molecular structures of those materials to the point where if they're load bearing, they can lose their ability to bear weight, and this can cause buildings to collapse. And also, if those buildings contain water pipes, those water pipes typically may be made of conducting materials, and the flow of this massive amount of electric current through those pipes can heat them up to the point where the water flash heats to superheated steam, bursting those pipes and causing even more damage. So during a thunderstorm, you should ideally disconnect all television aerials, those of you who still have television aerials, because this can act as a lightning conductor, which can then set fire to the TV. Sky dishes and satellite dishes are earthed to buildings to protect the satellite receivers and the TVs typically. So, as I mentioned before, static electricity poses a real problem when computers or printed circuit boards within devices generally are manufactured, upgraded, or mended. So, those of you who are PC enthusiasts and you upgrade your PCs or Macs, you typically should be wearing a wrist or heel strap. Apologies for the typo here, should say heel, double E. And so the reason why you wear these straps is to ground any static charge that builds up on the surface of your body, preventing it from discharging into the components of the machine as you are upgrading it and making physical contact with it. Now, again, it's typically the memory or RAM chips within these devices which are most at risk because they're not directly shielded in any way. So static discharges can damage RAM chips permanently. So those of you who work on electrical devices, particularly sensitive printed circuit boards in laptops or phones, you should be wearing these static wristbands around your wrists or around your ankles to protect against that kind of damage to your equipment. So this operator that you see here in this photograph is wearing a wrist strap as she inspects this circuit board, which is grounded in this manner. So another application of electrostatics is electrostatic precipitators. Now you find these in power stations which burn things like coal, which produce large amounts of smoke. Now smoke is not what you're seeing coming out of these so-called smokestacks. You're actually seeing water vapor coming out because there are very strict laws against allowing smoke particles to come out. And the way that the smoke particles are filtered out of the exhaust of these fossil fuel power stations is by the use of devices called electrostatic precipitators. Now, these use several thin, positively charged wires drawn out across the center of the power station chimneys, The wires are charged to about 50,000 volts, and the electrostatic field surrounding the wires makes the smoke particles positively charged as they pass by them. So the positively charged smoke particles are then repelled by the wires, forcing them towards the earthed metal plates where they collect. So every few minutes, an automatic hammer will then hit the plates, and then the ash that is collected on them falls down into a container and is then removed. So this is showed here by this diagram. So here we have the chimney wall. This is the inside of the chimney of leading from the power station where the exhaust gases are rising up. Here we have the positively charged wires, and we have the earthed metal plates on the sides of the chimney. So what happens is the smoke particles, as they rise up, have positive charges on them, and this causes them to adhere to these earthed metal plates. Now, the metal plates contain mobile electrons, and so as the positively charged particles come up near them, this repels or this attracts the negatively charged electrons to the near surface, and then this causes these positively charged ions, the smoke particles, to adhere to the surfaces of the metal plates. Once in every while, a hammer will automatically hit these plates, and this causes these dust particles to fall down into a collector, which then can allow us to remove those particles. So in this manner, the exhaust gases coming from coal-burning power stations are very effectively cleaned and smoke is removed. So if ever you see these photographs of the big chimney stacks, which a lot of people call smoke stacks, in fact, they're not smoke stacks. That white mist that you're seeing rising up from those smokestacks is pretty much all just water vapor. So we've talked a lot about static charge. Now, the reason why static charge is so important is because, again, electric current is defined as the average flow of electric charge in one direction through a material or even through a vacuum. You can have a beam of electrons traveling through a vacuum in one average direction. You still have the average movement of charge, and that would still be described as an electric current. Now, another one of these common misconceptions that I often run across is that electricity travels at the speed of light. Well, the energy transferred by an electric current around a circuit effectively travels at the speed of light, but the electrons themselves are moving relatively slowly. The electricity, which is the transfer of electrical energy, travels roughly at the speed of light. In a conductor, like a metal, so say, for example, the wires in an electrical circuit, but much slower in insulating materials. An electric current is the flow of charge, and the charge in this case is carried by electrons. So the movement of charge around a circuit is caused by a force which is provided by the voltage supply. And so this can be an individual cell or a battery of cells. And so this power supply provides the motive force which pushes the electrons around the circuit. Now, again, this is somewhat of a simplification, but it is essentially useful for GCSE level physics. So before we go any further then, let me just remind you of one of the basic ideas that we need to home in on here. So the idea of voltage causes people a lot of problems because it's not something that you can directly visualize. So voltage, like many quantities in physics, is defined in terms of equations. So one of the important things that you need to be doing for your revision is making sure that not only do you memorize your equations, because the way that specifications work now, you're not going to be provided with all the equations that you need in the exam, and you have no way of predicting which equations you will be provided. And so really the only answer for you is to memorize them all and make sure not only that you've memorized them, but that you've had some practice rearranging them and applying them to problem solving. So another reason in particular in physics why it's very useful to be familiar with both the equations, having them memorized, and also rearranging them is because equations in physics have this useful property of being able to give you the definitions of key terms like voltage. So the equation that you need to know, one of the equations that you need to know that contains the term voltage, is that the voltage is defined as the work done per unit of charge that flows between 2 points in a circuit. So if we imagine we have a certain charge over here, let's just call that charge Q in coulombs. If that charge moves between this point here to this point over here, then the work done in moving the charge from here to here per unit of charge, so if we imagine that the charge here, Q, is 1 coulomb, 1 unit of charge, then this number here simply becomes 1. So the voltage is defined as the work done, and work is the amount of energy transferred by a force which moves this charge from this point, point A, to this point, point B. The amount of work done, if this is 1 coulomb of charge, if the amount of work done in moving this object from this point to this point is W, then the voltage is W. So voltage, if we see this equation, we can just literally translate this equation into a statement, into a plain English statement, which defines what voltage is. So voltage is defined as the work done. Now, work, being a measure of the transfer of energy, is measured in joules. The work done in moving a unit charge, 1 coulomb, between 2 points. Now, that can be 2 points in a circuit, like this one, or it can just be 2 abstract points in space that we happen to be talking about. So if we imagine we close this circuit, the electrons in this circuit are flowing from the negative pole of the power supply, where they are in excess, to the positive pole of the power supply. So this is the actual electron current. So if we were to take this point where they emerge from the power supply and this point where they return to the power supply, the work done in moving 1 coulomb of charge around the circuit from this point to this point is the voltage of the supply. And this is what we mean by voltage. That's basically the formal definition of voltage. Now, for added hilarity and difficulty for students, unfortunately, this is the electron current. This is the actual flow of charge around the circuit as it actually happens. However, long before electrons were discovered, people were aware, physicists and engineers were aware, that some form of energy was being transferred around the circuit, because after all, if the bulb lights up when we close the circuit and the bulb is transferring energy as light from the bulb to the surroundings, then something must be carrying energy from the electrical energy supply to the bulb. However, at the time, they didn't know about electrons. And so by convention, they said that the current, the flow of electrical energy, was from the positive pole to the negative pole. So we say that the conventional current is from the positive pole of the power supply to the negative pole, and this has determined the, for example, the symbols that we use for certain electrical devices, because those electrical devices like diodes, for example, were discovered before we knew that, in fact, the electron current, the actual flow of charge, is in the opposite direction to the conventional current, which is considered to be from positive to negative. So basically, in all examples where you are expected to consider the current flowing around the circuit, unless you are specifically considering the electron flow, you should consider the current to flow from the positive to the negative. And we're going to be seeing examples of this both in this topic and also other topics within this series of webinars, like, for example, the energy topic, the electromagnetism topic. In almost all cases, unless you're specifically considering the electron flow, you should consider the current, the electric current, to flow from the positive pole of the battery or the cell to the negative pole. Okay, so now I'm going to finish the first hour on this concept, and we'll continue in the next hour here. So to appreciate how a flow of electrons can create an electric or can carry an electric charge, we need to use analogies. Unfortunately, visualizing things like voltage, electrons, and things like that, it's very difficult for us to have any real parallels to the kinds of things that we see in our everyday world. And so to really understand these things, we sometimes need to make use of analogies. So let's use an analogy where a simple circuit like this one is somewhat analogous. We can compare it to a domestic central heating system where you have the pump, which is pumping the water through these pipes and also heating the water before it's pumped through the pipes. And then the water reaches this radiator board, which then radiates some of the heat energy from the water into the surroundings. And then the water is returned by the pump to the pump and the boiler where it's heated again. So we're using this as an analogy to understand the way that the electric current behaves in a circuit. So in this analogy, the pump and the boiler is analogous to the power supply in an electrical circuit. The radiator board is analogous to things like bulbs and buzzers or other devices which transfer the electrical energy carried by the electrons to the forms of energy which those devices emit. So a domestic central heating system produces heat. An electric bulb produces light. In the central heating system, the boiler transfers heat energy to the water molecules inside the system. The boiler's pump pushes the water through all of the pipes. Now, in a lighting circuit like this one, it's the battery or the power supply, the cell, which transfers energy to the electrons, electrical energy to the electrons, and then pushes them through the electrical conducting wires to the devices, which will then transfer that electrical energy into other forms. So in this analogy, we have the power supply in the electrical circuit is analogous to the boiler and pump in a central heating circuit. The electrons, and again, we're showing the conventional flow of current here, the flow of electrical energy. The electron flow would actually be in the opposite direction. But in this analogy, the water molecules inside the domestic central heating system are analogous to the electrons flowing around the electrical circuit. So the metal pipes in the central heating system allow the hot water to flow through them. The electrical wiring allows the electrons to flow through them. So again, in this analogy, the pipes in the central heating system are analogous to the metallic conductors, the wires which make up the electrical circuit. So when the hot water passes through the radiator, some of the thermal energy of those water molecules is then transferred as heat to the surrounding atmosphere, the molecules of air in the room. In a lighting circuit, the lights in the circuit, the bulb or the lamp, transfers the electrical energy carried by the electrons to light and a little bit of heat energy in the surrounding atmosphere. Now, the volume of water flowing around the system at point A and point B in this central heating circuit would be the same at both points because you're not losing water to the environment. It's a closed loop. So if we measured the number of water molecules flowing past this fixed point here, point A, we would find that it's the same number of water molecules per second flowing past this fixed point B. In a similar way, in a series circuit, if we pick any 2 points in a series circuit and measure the number of electrons flowing through them per second, we would find that it's the same number of electrons. Water molecules are not being lost or being added into the system here or here. Electrons are not being lost here or here. And so the number of electrons flowing past this fixed point per second is going to be the same number of electrons flowing past point B per second. So the current, the flow of electrons, is the same at points A and B. But in the same way as the water loses energy between points A and point B to either side of this radiator board, the electrons are transferring some of their energy into light and heat as they flow through this device here. So I'm going to skip past this. In the replay video, there will be a pop-up question where you will be able to have a go at this passage yourself. But for the moment, I see that we've reached the end of the first hour of this webinar, so I'm going to take a brief 5-minute break. Again, in keeping with the format of the webinars as advertised, at the end of the second hour, if you'd like me to continue for an extra half hour, I will do so before the half-hour Q&A, but I'll leave that up to a vote at the end of the second hour. So in this next hour, we'll finish off talking about electrical circuits. If you want me to go into the exam questions, I'll let you guys vote yes or no. If you want me to continue with the teaching, I'll let you vote yes or no. Again, any topics that we don't get time to cover in this webinar, you obviously have the webinar private resources page for attendees, where you will have 24/7 access to ask me questions either in the public chat, or you can send me a private question by typing a note here and then checking this box to say notify your teacher and then sending me that message, and I will respond within 24 to 48 hours. So I can see that there's been a lot of questions posted in the Q&A. Again, because you're all in private separate rooms, you will only see the questions that have been posted by the people in your webinar room. So if you're from a particular school, you will only see the Q&A questions that have been posted by other members of your school. But I can see that there have been actually some quite interesting questions. So keep those questions coming, and I'm going to break here for 5 minutes and give you guys a bit of a breather. After the 5-minute break, we'll come back and we'll continue for another hour, and then I'll give you guys the option if you want to continue for a further half an hour. So I'll see you in about 5 minutes' time. So we're back after the 5-minute break, and we will continue just for a bit longer. So we'll cover the idea of electrical circuits, and then we'll get into the exam questions, depending on what you guys want. And again, I'll let you guys vote on that. So now that we've talked about what we mean by electron flow in a circuit, and we've kind of used an analogy to explain what we mean by that, it's important, again, not for you to not just know your units for or the equations. You need to also understand the units for these quantities that we're talking about here. So electric current is measured in a unit called amperes. Now, again, going back to the equations that you need to know, and we'll talk about this shortly. If the voltage is the work done per unit of charge moving from one point to another, the current, which is measured in amperes. Now, amperes is abbreviated to amps. This is the unit of current. Now, current is given the symbol I in physics. So just remember, the I means electric current. So electric current is defined as the flow of charge past a fixed point per unit of time, and the unit of time is the second. So again, we have an equation that you need to know, but this defines for us what we mean by electric current. So electric current is the flow of charge, but specifically it is the amount of charge flowing past a fixed point per unit of time. So again, we can define current. Current is defined as the charge in coulombs which flows past a fixed point per second per unit of time. And this is a literal translation of this equation. Whenever you see a divided sign, we can translate that as being per something. So current is defined as the charge per unit of time, in the same way that voltage is defined as the work done per unit of charge. So again, it goes back to this idea that it's very, very important for you to memorize the equations, but also just specifically in physics, the value of memorizing equations is not just that you get to just solve problems with them, it's because the equations themselves allow you to not have to memorize the definitions for these things. You can simply translate what the equation is saying into English, and that will give you a very good, rigorous definition for these terms like voltage and current that we've seen here as examples. So, electric current. The important thing is, another one of these misconceptions that I see all the time in exam questions and the answers to exam questions is the idea that electric current is somehow used up by the devices in a circuit. Now, as we saw before, the amount of charge which flows past a fixed point on one side of an electrical device like a bulb is going to be the same amount of charge that flows past the fixed point on the other side of that bulb. The electrons don't disappear and they don't appear from nowhere in the circuit. So the electric current is not used up by the components in a circuit, but it transfers energy from the voltage source, the power supply, to the various components making up the circuit. Now, electric current, hopefully you know by now, is measured using an ammeter. And so the symbol for an ammeter is shown here. And ammeters are always placed in series with the electrical components in a circuit. So again, calculating current, the current passing along a wire can be calculated using the formula that you saw before. I is equal to Q over T, like this. But if you need to rearrange the equation and you're not too confident with your algebra, you can always use one of these formula triangles. Although if you really are aiming for those top grades, ideally you should be confident with just memorizing the equation and then being able to rearrange it algebraically. So if we wanted to rearrange this equation to make charge Q the subject, we would multiply both sides by T, and we get Q is equal to IT. If we wanted to rearrange the equation to make T the subject, we would first multiply both sides by T and then divide both sides by I, and we get this, T is equal to Q over I. But either way, you can use this formula triangle if you struggle with that. So the current passing along a wire can be calculated using the formula charge is equal to current times time, and we rearrange that to I is equal to Q by T. So we can also use this formula to do some calculations. So for example, we can rearrange to calculate the charge passing through an appliance, the length of time an appliance is switched on for. If you do rearrange it for time, just remember the standard units are the units that you need to be entering into the equation. And if you're solving for T, then the solution, if you've entered charge in coulombs and current in amps, the solution is going to be in the units, the standard units of time, which are seconds. So if you need to convert that into hours or minutes, you will need to do so. Always enter your values into an equation in standard units by default, unless you have a specific reason to do otherwise. Otherwise, the answer that you get from that equation will not be correct. Just remember that. So it's very important not just to memorize the equations and how to rearrange them. It's also important that you understand and remember the standard units for the quantities in those equations. Time is standard units is seconds. Charge, the standard units are coulombs. Current, the standard units are amperes. So if you know any two of these values, we can rearrange the equation or use the formula triangle to find the third or unknown value. So here's an example here. So if we have a charge of 40 coulombs passed through an electric sander when a 2 amp current flows, how long was the sander switched on for? So you can give your answer in standard units of time, or if you prefer in some other non-standard unit, but always show you're working out. So again, for those of you watching as a replay recording, the question will pop up, so you can go ahead and have a go at that. If you see the question pop up on your screen right now, then go ahead and have a crack at that. If you're not seeing this question pop up, then you can just use the chat box to answer this question. So I'll give you a few seconds to have a crack at the answer to this, and then I'll show you the solution, and then we'll move on. So see if you can solve this question. How long was the sander switched on for? Okay, got quite a few people quick off the mark already. Well done. You don't need to show the full working, but obviously in a real exam you would show the full working, and we're going to go through some exam questions in a short while here. Okay. A lot of people are converging on 20 seconds. Very good. A few more seconds. This sort of question shouldn't take you more than a few seconds to work out and then answer. But don't worry, you'll get plenty of practice. And again, those of you who've had a go at the exam questions already will notice that there's quite a few questions which require you to do and apply this equation. So let's have a look at the solution then. So I want you guys to get into the habit of using a very rigorous and systematic approach to answering exam questions. You must, and again I stress this, please, 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 regardless of what target grade you're going for, regardless of how, what your current working out level is, your first port of call is to memorize your equations, memorize the standard units for all of the quantities in those equations, and get lots of practice rearranging those equations, whether by use of these formula triangles or by simply knowing how to rearrange the equations algebraically. The reason is that over and above the reasons I've already given you for doing these things, is that there is a very systematic approach that you need to adopt when you're answering questions like this, calculation questions in exams. And this applies to physics, biology, or chemistry. The very first thing that you should be doing is writing down the appropriate equation, preferably rearranged to make the desired quantity, in this case time, the subject. So the first thing that you do, even if the equation already appears in the answer sheet, of course that should make no difference to you, you should have already memorized it. The first thing you do, show the examiner the equation. In this case, we're solving for time, and so time is equal to charge divided by current. The next thing that you do is you substitute the quantities into the equation in standard units. Now, luckily, in this case, we've been given the charge in coulombs and the current in amps, which are standard units already. So again, in the next line, write down the substituted values. Now, again, I want you to get into the habit of writing down each step of your working on a separate line. Do not write equals 40 coulombs over 2A. Although that wouldn't be incorrect, it's messy. It's not a kind of classically rigorous way of showing your answer. Try and use the guideline that the next line should always show the next step of your working, and the equals signs should be vertically aligned with each other like this. So we substitute our values, we then evaluate, and we give the answer in standard units. So well done to those of you who said 20 seconds. The sander was switched on for a total of 20 seconds. Well done. Okay, so power is another one of these quantities, which is a very general concept in physics. Now, before we talk about power in electrical circuits, let's define what we mean by power, generally speaking, in physics. Power is a concept which you're going to come across in lots of different types of systems in physics. Here, in this topic, we're considering electrical systems, but a system can be any object or group of objects. And so we can talk about power in mechanical systems, we can talk about power in various other types of systems. The general definition of power is a measure of the work done per unit of time. So power in general, this applies to all systems. Power is always the energy transferred divided by the time taken to transfer that quantity of energy. So it's essentially the rate at which energy is transferred. And this is the general equation for it. Power is equal to work done divided by time. And so once again, we can define what we mean by power by simply translating exactly what this equation says into plain English. Power is defined as the work done per unit of time. So another way of talking about that is the energy transferred, or the rate of energy transfer. Whenever you're dividing a change in some quantity by the time taken for that change, you're describing the rate of change. So the word rate is another one of those words that you really need to be familiar with, because you're going to come across it in all kinds of exams, physics, biology, chemistry, and possibly even other exams as well. So here we can see that power is the rate of work done, the rate at which energy is being transferred. Current is the rate at which charge is transferred. So another way that we could define current is the rate of transfer of charge. So whenever you see something divided by time, the change in some quantity divided by time, you're talking about the rate at which something is changing. So power is the rate at which energy is transferred in general. In general, in all systems, it can be described as being joules per second. So again, looking at that equation, if work done is a measure of energy transferred, work done is always measured in joules. Time, standard units are seconds. So power can be described as energy transferred per second, in other words, joules per second, but we use the unit watts to be equivalent to that. So 1 watt of power is equivalent to 1 joule being transferred per second. So the power of any electrical appliance can be calculated if you know the amount of energy transferred and the time taken to transfer that quantity of energy. But this is the general equation for power. In electrical circuits, typically we may not know the amount of energy transferred. We may know the voltage, we may know the current, we may not even know the time for which that device has been switched on. So there are other equations specifically in the context of electrical circuits which are used to calculate power. So the power of any electrical device can be calculated from the potential difference across it, the voltage, and the current flowing through it. So the relationship is shown in this equation. So this is a specific equation which relates power to quantities concerning electrical circuits. So a lot of the time in physics we have general equations which describe in general for any system a particular quantity and how it's calculated. So in all systems, energy is transferred and time is taken for that energy transfer, whether you're talking about mechanical systems, electrical systems, whatever. So this is the general equation which defines what we mean when we say the word power in physics. But in different systems, like electrical systems, power is transferred differently and is related to other quantities which are specific to those systems. So quantities like voltage and current are specific to the description of electrical systems, and so it's useful to have an equation which relates power to those quantities. So power is in the electrical context can be calculated like this. It is the product of current and potential difference across a device. So again, the standard units for these are watts, amps, and volts for power, current, and potential difference respectively. So the equation is P is equal to I times V, and of course we can rearrange this equation either algebraically or, if you prefer, with one of these formula triangles. To get I, we divide both sides by V. To get V, we divide both sides by I. So we can calculate any one of these quantities when we know the other two by rearranging the equation. So let's take a look at one example here. So when a 100-watt light bulb is switched on in a room, the light given out is very bright. The bulb is converting 100 joules of energy per second from electrical energy, which is the input, to other forms of energy, in this case light and some heat. But the power rating, 100 watts, describes the total energy transferred from the input form to all of the output forms per second. However, if we compare this to a 40-watt light bulb in the same room, the light emitted is not as bright. Now, this is because the bulb is only converting 40 joules of energy per second into heat and light. The 100-watt bulb has a higher power rating and produces more light per second than a 40-watt bulb. So, when we imagine an electrical current flowing through a wire, not sure why this is happening, in an electrical heater, the heat energy is the desired energy output. Now, this goes to a concept called efficiency. Efficiency depends on a couple of things. It depends on what is the desired energy output, the useful energy output for that device. Going back to the example of light bulbs, when you buy a light bulb, your intention is not to heat the room with it, although the light bulb does produce a heat output. The heat output in that case is wasted or dissipated energy. But in the case of an electrical heater, heat is the desired output. It's the desired energy transformation from the input form of energy, which is electrical, to the output form of energy. So the transformation of electrical energy is related to the potential difference and also the charge. So again, this is another way of describing that same equation that we saw in the previous hour where we defined what voltage is. The energy transferred is the work done. The charge which flows due to that energy transfer, due to that work done, is the value Q. So in this equation, this is how it appears in some, not all, of your GCSE Physics specifications. Rather than saying V is equal to W divided by Q, they'll use the term E to stand for energy transferred, but it's the same equation. Voltage is defined as the energy transferred, or the energy required to move 1 coulomb of charge from one point to another in the circuit. So again, you can use this formula triangle to rearrange that equation. So again, remember, energy transferred or work done is always measured in joules because you're measuring a quantity of energy, regardless of the means by which energy is transferred or stored. The magnitude of that energy transfer or storage is always measured in the standard units of energy, which is joules. Potential difference is measured in volts, and the standard unit of charge is the coulomb. So we can use the formula triangle, and once again, if you know any two of those values, you can use the formula triangle to find the remaining value, or hopefully you will get enough practice memorizing these and rearranging these equations that you won't need to use these formula triangles. So here's an example for you to have a go at, and again, if you're watching this as a recording, the This question will pop up on the screen shortly, so you can have a go at this. If you're watching this live, my attendees currently, if you see the question pop up on the screen, go ahead and pick one of the options. If you're not seeing the question pop up on the screen, go ahead and type your answer to this question in the chat box, and I'll give you a few seconds to have a go at this. So, a 1 kilowatt iron was used for 10 minutes. How much electrical energy was transferred given that mains electricity is 230 volts? So 230 volts is the mains voltage for mains devices like this iron in the UK. So there's your question. Have a few seconds, have a go at this question for yourselves, and see if you can come up with the answer. Now, this question does contain one extra wrinkle. I'm not going to say what that is, but I'll give you a clue. Just remember standard units. So have a go. All right, so again, mains electricity is 230 volts. So if we are considering that it's a 1 kilowatt iron, then we can say that a current of 4.35 amps flows through a 1 kilowatt iron. So let's have a look at how we calculate the energy transferred. So power is equal to energy by time, or energy transferred or work done by time. So if we rearrange this, we get the energy transferred or the work done is power multiplied by time. Now, the wrinkle in this question is the units. You're being supplied with the time taken, not in standard units of seconds, but in minutes. So you need to convert this into seconds before you enter it into this equation. So we have here 10 minutes, and the energy transferred is going to be the power, 1 kilowatts, 1000 watts, multiplied by 10 times 60, because there are 60 seconds in every minute, and it's on for 10 minutes. So 10 minutes, 600 seconds, and so this gives us an energy transfer of 600,000 joules, and we can convert this to kilojoules, 600 kilojoules. So in 10 minutes, 600 kilojoules of electrical energy was transferred. So now, a lot of exam questions will give you some information which may not be immediately relevant to the question. There may be, particularly the higher mark questions, there may be information which is being provided to you which you may not need to answer the question. So I gave you the information that there's 230 volts, but this would only be useful if you knew the current flowing through the circuit. Now, you can calculate the current. I'll leave you guys to see how you could do that, but you may need to use more than one equation to do so. In this case, it's a fairly straightforward problem. The only slight wrinkle is that you need to convert from watts to kilowatts to watts, which is standard units, and you need to convert from minutes to seconds, which are the standard units of time. So voltage, as we said before, is supplied by batteries, cells, power supplies. It's measured in volts, and this is an electromotive force. Now, electromotive force is the kind of an old-fashioned way of describing what voltage actually is. Voltage is defined as the work done per unit of time, or rather per unit of charge, which moves through or between two fixed points in a circuit. However, in order to move an object like an electron, you need to push it or pull it. You need to apply a force. So that work is being done by a force which moves the electron from one point to another point through that conductor. And it's the power supply which provides that electromotive force. So the voltage across a circuit component, so for example a bulb which is converting electrical energy into heat and light, is a potential difference. It is a difference in potential between one side of the device and another, and it's that voltage, that potential difference, which provides the force which does the work in moving the electrons through that device between those 2 points. So potential difference is also measured in volts. The potential difference is a measure of the energy carried by the charge flowing within the circuit. So within electrical circuits, the difference in electrical potentials across different components will drop as each component converts some of that electrical energy into other forms of energy. Potential difference is measured using a voltmeter, and a voltmeter, unlike an ammeter, is not placed in series, it's placed in parallel to that device. So if we wanted to measure the voltage of a power supply, say this battery of 2 cells here, we would connect the voltmeter in parallel across those two devices. So note the language that I'm using here. Voltmeters are connected across a device that you're measuring the potential, because you are measuring a potential difference. You're measuring the difference in the energy carried by the electrons here versus the energy carried by the electrons here. The electrons are emerging from the power supply at the negative pole. They're carrying energy to the devices in the circuit, in this case the light bulb. Those devices then use that energy by transferring it from electrical energy carried by the charged electrons to other forms. The electrons emerge from this other end and then return to the power supply carrying less energy. And so the voltage is a measure of the difference, the potential energy difference of those electrons from one point in the circuit to another point in the circuit. And so because you're measuring a potential difference, you can't connect it in series, you have to connect it in parallel, because you're measuring the difference in energy of the electrons between 2 points. So, one final point actually is that the switch does not need to be closed. You do not actually need to have an electrical current in order to measure the potential energy difference across a power supply, such as a battery. So another quantity that you need to be aware of is the idea of electrical resistance. So resistance is defined as the property of materials which restricts the flow of electricity. So if you're ever asked for a definition of resistance, this is a good definition for you to memorize. There are very few definitions in physics which require you to memorize a verbal definition which you can't really easily deduce from an equation. Now you can define resistance in terms of other quantities that appear in equations with resistance. However, at GCSE level, I would thoroughly recommend that you memorize this definition for the term resistance. So energy is converted into other forms as the voltage across a component drives a current through it. So for example, again, a lamp or bulb will convert some of the electrical energy carried by the electrons flowing through it into heat and light energy. So the standard unit of resistance is the ohm, and we use the Greek symbol omega to denote the ohm. So what causes resistance? Well, as we saw before in that animation of the flow of electrons through a metallic conductor, as an electric current flows, charged particles, the electrons, are moving through the conductor, but these charged particles, the electrons, in doing so, will collide with the ions or the atoms making up that conductor, and this makes it more difficult for the current to flow, and this is what causes resistance. So, for example, there are a lot of different quantities, there are a lot of different parameters or properties of materials which will affect the resistivity of those materials, the amount of resistance that electrons will, an electric current will experience going through a certain amount of those materials. So, for example, longer wires causes an increased resistance, and this is because the electrons will collide with atoms more often in a long wire than in a short wire. Also, if you have thinner wires, this will increase the resistance also because there are fewer electrons to carry the current than in a thick wire. So the ohm was named after this gentleman here, Georg Simon Ohm. So he in the mid-1800s, he based his work on conduction in metal wires, and he formulated a law which related the current passing through a wire and the potential difference or the voltage applied across the wire. So he found that for a fixed temperature, the current flowing through a resistor is directly proportional to the potential difference across the resistor. So voltage is equal to current times resistance, and this became known as Ohm's law. Ohm also introduced the standard unit of resistance, the ohm, and again we use the Greek symbol omega to denote the ohm. So again, if you need one of the formula triangles to rearrange this, you could use this one. Voltage is equal to the product of current and resistance. If we want to make current the subject, we can divide both sides by resistance and we get this. If we want to make resistance the subject, we can divide both sides by the current and we get this. So Ohm's law as with all of these similar format of equations, if you know two of these quantities, as long as you have them in standard units, you can rearrange the equations, substitute them in, and find the third unknown quantity. So let's look at an example here. A 10 ohm resistor is placed in a circuit with a potential difference of 5 volts across it. How do we calculate the current? Well, again, I want you to get into the habit of doing this. Show the equation rearranged for the relevant variable here. So the current is I, so we need to rearrange as so. So we show the examiner, I is equal to V over R. We then, on the next line, substitute our values in standard units, 5 volts, 10 ohms. We divide that and we evaluate and we get 0.5 amps. So the current in this case is 0.5 amps. I'm going to go ahead and show you this slide here. Okay, so if we now increase the resistance, and again, by Ohm's law, if you increase the resistance, then you are going to decrease the current. Now, you can arrive at that conclusion either using Ohm's law. So again, thinking about it with Ohm's law, current is equal to voltage divided by resistance. If the voltage remains the same, but the resistance is increasing, then you're dividing a constant number on the top of that fraction, the voltage, by an increasing number on the bottom of that fraction. So if you now increase the resistance, you can see that we are decreasing the current. But you can also arrive at that conclusion intuitively because, again, if you go back to that definition I gave you for resistance, it's the property of a material that restricts the flow of electric current through it. If the resistance is higher, then the current flowing through it will be restricted. And as you can see here, if you compare the brightness of the bulb with a high resistance, 50 ohms, to the brightness of the bulb with a lower resistance, when you have a lower resistance, you have a brighter bulb. This is because the current flowing is higher, which means more electrical energy is being transferred to the light bulb per second for the light bulb to then transfer as light and heat energy. So for a fixed potential difference, in all of those examples, 9 volts was the potential difference. When you increase the resistance, you decrease the current flow through that circuit. Now, this is a series circuit, obviously, but the same would apply to any specific branch of a parallel circuit, as we'll see. So this is another one of those ideas that many of you voted as being one of the more kind of tricky ideas for me to cover. This is one of the ideas that received the most votes. So let's have a look at this. So current versus potential difference graphs. Whenever you see this kind of phrasing, X or Y versus X, Y against X graphs, Y always goes on the vertical axis, X always goes on the horizontal axis. So current against potential difference graphs, you always have current on the vertical axis, voltage on the horizontal axis. So these types of graphs will show you what happens to the current when you vary the voltage. So if you go from 0 voltage to a higher voltage, we see that for a fixed resistance, a fixed resistor, the current increases in linear proportion here. So the resistance of a fixed resistor remains constant as long as the temperature remains the same. So this is a control variable here. As long as the temperature remains the same, the relationship between these two variables is direct proportion, a straight line that goes through the origin. Now, the negative values of voltage represent when you change the polarity of the voltage supply. But if you then increase the voltage in the opposite direction, we see that the current also becomes increasingly negative, similarly in linear proportion. So this is the current versus voltage graph for a fixed resistor at a fixed temperature. Now, if we compare that to a filament lamp, the type of bulb which has a very thin filament of metal through the middle of it, this is a very different shape. Now, the reason for this shape is this. The resistance of a filament lamp increases as its temperature increases. This is due to the fact that as the lamp heats up, the metal ions in that metal move faster and more vigorously, and this causes the electrons to bump into them more frequently, and this in turn raises the resistance of the filament, and this then causes as the higher voltages are reached, the current does not increase as rapidly as at the lower voltages. And so this is the shape of the I versus V graph for a non-ohmic resistor or a filament lamp. A fixed resistor obeys Ohm's law, but a filament lamp is a non-ohmic resistor because its current versus voltage graph is not a linear proportionality. Now, if we compare this to a diode is a device which only allows an electric current to flow through it in one average direction. So if we increase the voltage in a particular direction, the current will increase. But if we reverse the polarity of the power supply and try and increase the voltage in the opposite direction, we get no current at all. A diode is a device which only allows electrical current to flow through in one direction only. And so the diode has a very high resistance in the reverse direction. So the diode acts as a one-way switch, effectively only allowing electrical current to pass in one direction through that part of the circuit. So, thermistors are another thing that cause a lot of students problems in understanding what they do. The resistance of a thermistor is actually dependent on the temperature, but perhaps not in the way that a lot of students seem to think. If you increase the temperature of the thermistor, we can see that actually the resistance of the thermistor decreases. And so if the resistance is decreasing, we're getting an increasing current, again, think of Ohm's law, and therefore more electrons are passing through the lamp per second, delivering in turn more electrical energy to be transferred into light energy per second. So if we compare that to another electrical device, which you should all be familiar with, the light-dependent resistor, whose symbol looks like this. A light-dependent resistor is a resistance or a resistor whose value of resistance in ohms depends on the intensity of light falling upon it. Now, in total darkness, its resistance is very high, and so we can see here that we have a very low current, 3 microamps. So this symbol here, this Greek symbol mu, this is the symbol for micro, which is a prefix which we put in front of a unit to mean 1/1,000,000th of that unit. So this is actually 3/1,000,000ths of an amp, 3 times 10 to the power minus 6 of an amp, a very small current. Now, if we increase the light intensity, if we shine a bulb on that, we can see that the resistance actually decreases, and therefore more electrical current is flowing around. Now we have 1,000 microamps. And therefore we have more electrical energy being delivered to this bulb by the electrons flowing through it per second. So a light-dependent resistor, an LDR's resistance, decreases as the light intensity increases. Okay guys, so that kind of covers the main topics that you all voted for me covering. Now obviously this topic of electricity does cover rather a lot more. I've only covered about 75 slides out of the total of 120 slides that cover this entire topic. However, on the private webinar resources page, I will make all of the slides available to you in this section here. So basically, let me just bring this up on the board here. So you will get all of the slides up to this point, but you'll also get the slides on the other aspects of this topic, which you didn't vote quite as much for. Parallel circuits, series and parallel circuits, and so on. So you guys can go ahead and use those for your notes. I'm going to, before we go into our next 5-minute break in about 8 minutes time here, I'm going to let you guys vote. Would you like me to continue for an extra half hour or so? Because obviously we need to get into some exam questions and go through the exam questions pack that you all received. Now, just to let you guys know, in terms of order of votes, most of you voted for me to go through question 3 first. So this is question 3. You asked me to go through question 3 because you felt that that was the most challenging question. That was closely followed by question number 2, and that was followed by question number 4, and that was followed by question number 5, and then that was followed by question number 1. So I will go through those in order in the next section. That's up to you guys though. So if you want me to go through the exam questions in the next half hour with a half-hour extension, then go ahead and say yes. If you would prefer me to just go into the question and answer session, because Many of you have asked a lot of very interesting questions. I will go ahead and just go into that question and answer session after the next 5-minute break. So I'll give you a few seconds to make your vote on that. And again, remember that whether or not you choose for me to go into the Q&A session or to go through the exam questions, the full mark scheme for this will be made available on that private webinar resources page in the next 48 hours, along with the slides. And also remember, you will still have access to ask me questions either in the live chat or private questions via the private notes, all the way up to your exam. So I'll give you a few seconds to vote on that, and I will either go through questions for the next half hour, then go through the Q&A, or just go straight into the half-hour Q&A after the next 5-minute break. So but I believe we've covered most of the topics that you all voted for, at least the first 4 out of 5 topics that you voted for me to go through in this section of your spec on electricity. So it seems like most of you would like me to go for an extra half hour on exam questions, which is fine. So let's go through those exam questions and then we'll get into the Q&A session. Lots and lots of good questions answered on the Q&A session. Now again, those of you who do need to leave, I appreciate that. Obviously the replay video will be on there, so you'll see me answering the Q&A questions on the replay video, so please do go if you need to go, but it seems like it's about 70-30 thereabouts. Most of the students, 70% of you also voted for me to go on for an extra half hour focusing on the exam questions. Now many of you on at least 3 of the schools who, or at least the students from 3 of the schools, of the 4 schools who are attending today, you are subscribed to privately published course modules which contain full teaching on all of these aspects of the electricity course. If you do have any questions about any of the remaining topics, which we didn't have time to cover in the first couple of hours, please do go ahead and use the live chat. Remembering, of course, that you are subject to the rules of the site, so please use that responsibly. Okay, so let's have a crack at some of these exam questions. So the one that you most of you voted for by far as being the toughest question here was, I believe, question 3. So let's have a look at question 3. So the diagram shows the structure of a cable. The cable is part of an undersoil heating circuit inside a large greenhouse. So first little point for you, when you're reading an exam question, please spend a bit of time looking at the context, the stem of the question, before you look at the bit of the question which actually asks you for things. So you're looking at a very simple context here. You've got an insulating sheath of material. You have a further insulating sheath which separates this copper braid acting as the earth wire. Now again, copper is a non-insulating material, and the 2 live and neutral wires here. So again, looking at this, we have 3 conductors. We have the copper braid, which is the earth wire, we have the live wire, and we have the neutral wire, and these are separated by an insulating material. So what is the frequency of mains electricity supply in the UK? The cable is connected to the mains electricity supply through a residual current circuit breaker. So this is the sort of thing that you need to be doing when you're reading an exam question. You need to read the stem, really take a look at the stem, and try and apply your existing understanding to that situation to give you some ideas before you even look at the part of the question that asks you the question. The other thing here is that it's bringing up a specific device that you should all be familiar with, residual circuit breakers. Now again, the slides that I'm going to make available to you do actually cover residual circuit breakers in the section on domestic uses and safety, which is the bit down here, where we talk about the 3 core cables, 3-pin wiring, safety devices such as residual circuit breakers. So please do have a look at those notes, which I'll make available to you, and go ahead and use those and ask me any questions that you wish in the live chat or the private questions here. So frequency of mains electricity supply is, of course, in the UK, 50 Hertz. Now frequency is usually measured in cycles per second, which is usually given the symbol Hertz. So let's just go ahead and use a pen here. I'll use a red pen. And again, I will make the mark scheme for this available to you. 50 Hertz. So what happens as the cable is cut to cause the circuit breaker to switch the circuit off? Now this is for 2 marks. Whenever you're answering an exam question, obviously pay attention to the number of marks, but also pay attention to the number of lines you're being given for your answer. Examiners take great pains to decide before they print and publish these exam questions what is the optimum answer and what is the optimum number of lines for a good student to give an excellent answer. And so when they give you a certain amount of space, it's never a random choice. It means something. Don't just pay attention to the number of marks available to a question, also pay attention to the amount of space you're being given to answer that question. So what happens as the cable is cut to cause the circuit breaker to switch off the supply? There's 2 marks, so you can assume that first of all you should take no more than 2 minutes answering this question. Usually it's about 1 minute per mark. And the second thing that you should assume is that you should be making 2 logical points. So one of these is that, first of all, some of the current flows down to the earth. Now you can also use the term ground. So some current flows to the ground or earth. Now, the second thing that you could say for a mark is that the current, because it's flowing to earth, it's going to be flowing through the copper braid. Right here in the stem of the question, they're telling you that this acts as the earth wire. So if you're going to be cutting through this wire, visually imagine what's going to happen if you take a blade and cut through this wire. Well, what's going to happen is you're breaking the insulation which separates these live and neutral wires from the copper braid and from each other. And so if the live wire is carrying current, that current is going to go through the earth wire, the copper braid, down to earth. So you can also score a point here by saying that the current flows to the ground or earth through the copper braid. So 1 mark for that. 1 mark for saying that it goes through the copper braid. An additional mark you can gain by saying that residual circuit breakers or residual current circuit breaker devices, the way that they work is by detecting the difference between the current in the live and the neutral wire. So we can say here that RCCB devices work by detecting a current difference between the live and neutral wires. So this would be an additional mark if you didn't get one of these first 2, but there's a maximum of 2 marks for this question. So that's part A, part 2. Let's have a look at part 3. So a circuit can also be switched off by the action of a fuse. Give 1 advantage of using a circuit breaker to switch off a circuit rather than a fuse. Now again, many examiners and many teachers hopefully will have drummed home to you again and again the importance of these command words. It's so important that you pay very close attention to what the examiner is asking from you, especially one of these command words. So give 1 advantage. What is 1 advantage of using a circuit breaker rather than a fuse? Well, there's a couple of things that you could say here to get these marks. Again, pay attention to the fact that you've only got 1 mark available. You've got 2 lines though. So I'm going to give you both things that you could have said to get these marks. First of all, an RCCB, a residual current circuit breaker, can be reset. So when a circuit breaker breaks a circuit, you can then flip a switch to reset it. You don't have to go replacing components in it. But a fuse, you have to physically replace the blown fuse after that fuse is blown in order for the current to pass through the circuit again. So obviously the fact that a circuit breaker can be reset is an advantage over using a fuse. So this would be worth 1 mark. Another thing that you could say is that an RCCB acts faster. to cut the circuit or break the circuit than a fuse. Now again, the reason you put a fuse in series with an electrical device is so that you're protecting that electrical device from too much current going into it. What happens is that the current flowing through the wire in the fuse melts the wire if that current is above a certain value. And in this way, a certain amperage fuse, like a 3 amp fuse, will protect the circuit behind it by preventing anything more than 3 amps from flowing through that circuit. But fuses have to heat up and melt and break in order to protect the circuit. And in that time, if you have a particularly high power surge, you can still damage components in the circuit before the fuse breaks and switches off the current. An RCCB acts more quickly than a fuse, and this again is an advantage. So either one of those would get you the mark for that one. So here is the bit that most of you seem to struggle on in this question. The 230 volt mains electricity supply causes a current of 11 amps to flow through the circuit. Calculate the amount of charge that flows through the cable when the cable is switched on for 2 hours and give the unit. So this is another thing that a lot of students will struggle with. Very often, exam questions, like for example this one, will give you the unit at the end of the answer section for the question. Here they're giving you the unit of joules, but in this case they're specifically asking you to give the unit as well as the correct answer. You're being given 3 lines to show you're working, you're being given 1 line for your answer, and there is no unit here. So you can assume that one of these is for the correct unit for charge, which is of course coulombs, the standard unit of charge. So we can go ahead and straight away write coulombs here, because we know that the standard unit is going to be in coulombs. Now, in this case, you're going to need to calculate the amount of charge that flows through the cable. So we're going for charge. Charge is Q. The cable is switched on for 2 hours. Now, the standard units of time are not hours, but seconds. And so, again, we need to convert from hours into seconds before we use any specific equation. But remember, the rigorous method that I'm trying to get you guys to follow is give the equation rearranged appropriately to calculate the quantity that you want before doing anything else. So, a good way of going about this is read the question, have a look at the quantities you're being given. You're being given voltage, you're being given current, you're being given the time taken in non-standard units. So, and you're being asked to calculate charge. So you need to ask yourself at this point in reading the question, which equations do I know which links current, voltage, charge, time, and which one can I use, or if I need to use more than one, which ones do I need to use to calculate charge? Well, we've already seen a couple of equations that link some of these quantities. We have the current is defined as we see here, the charge per unit of time, Q over T. We're trying to calculate charge in coulombs, and charge is Q. So we need to rearrange this equation to make Q the subject. So we would rearrange it by multiplying both sides by T to get rid of this T, so we can write the equation for the examiner straight away. Q, charge, is equal to the current I multiplied by T, the time in seconds. However, the time here is being given as 2 hours. So to convert into seconds, we need to multiply 2 hours. Now there are 60 minutes in each hour, so 2 times 60, and there are 60 seconds in each minute, so we need to multiply by 60 again. And so this gives us the time taken in seconds. So if we bring up a calculator just to show us calculating this, we have 2 times 60 times 60 again, 7,200 seconds. So this is the time taken, 7,200 seconds. So now we have our time in standard units. We already have the current in standard units, so we can now just go ahead and substitute those values into our equation. 11 amps multiplied by 7,200 seconds. So we multiply this value here times 11, and we have 79,200 coulombs. So this is our answer, 79,200 coulombs. Now, you must give both the answer and the correct units in order to get the full marks for this question. So in this particular case, if you did not give the correct answer, but you showed the correct substitution for both calculating time and also the substitution into the equation, then you will get 2 of the available 3 marks. And this is one of the values of showing your full working. It's that if you somehow mistype things into a calculator in the heat of battle in an exam, you will still get most of the marks if you show a correct working, even if you don't get the correct numerical answer. So part 2, calculate the energy transferred from the cable to the soil in these 2 hours. Well, so we need the energy transferred, but we were given the volts. So in this case, we need to make use of the correct equations for this. So again, think about the method that I've shown you already. We need to calculate energy transferred. Another term for this is work done, isn't it? So work in joules. We have the time in hours, but we've already calculated that 2 hours is equivalent to 7,200 seconds in standard units. Always use standard units in your calculations in your equations. So what we need is something that can allow us to calculate the energy transferred versus the time taken, given that we've just calculated the charge that's flowing. So here is a question for you. So I'm going to pause here and allow you guys to answer. If we need to calculate the energy transferred, the work done, and we know the charge, we know the voltage, we know the current, how would we do this? So what do you guys think? Okay, already some suggestions. So some of you are saying that, again, good, you're following the correct method. So remember, power is energy transferred by time taken. Well, how do we calculate power? Because we don't have the power. We have time. We don't have the energy transferred. We're trying to work that out. So we can't use the general equation for power. There are other equations for power, though. So again, going back to this is the general equation for power. But there are other equations. One of them that we've mentioned, good, many of you have already suggested this. I think my my graphics tablet is deciding that it doesn't like me using Microsoft applications as well as Adobe applications. So bear with me a second here where I get it up and running again. There we go. So that should work. Okay, so power in an electrical circuit, I say should work, obviously isn't. Let's try that again. There we go. So power is equal to voltage times current. Good. So if we wanted to work out the power is equal to voltage times current, but power is also equal to work done divided by time. Now what this means is, if you know both of these equations, and you should, because you should memorize them, you can equate this to this. They are both equal to power. So if both of these are equal to power, they must be equal to each other. So we can write voltage times current is equal to work done divided by time. Now, if we have this, going back here, so we have voltage times current is equal to work done divided by the time taken. Now we can calculate the energy transferred, the work done, because if we want to rearrange this to have W on its own on one side, we need to multiply both sides by T. So we have work done is equal to V times I times T. And now we can simply substitute our values. We have work done, which is what we're trying to work out, is equal to the voltage, 230 volts, times the current, 11 amps, times the time, 7,200 seconds. Nope. So if we evaluate this, 230 times 11 times 7,200, we get 18,216,000 joules. So 216,000 joules of energy. So this is our answer, 18,216,000. So some questions require you to know more than one equation, but if those equations are giving you have the same term as their subject, you can equate the other side of those equations to each other, and then you can simply substitute the values. So I think this was the one part of this question that most of you found particularly challenging. But there's your solution. So finally, the heating circuit includes a thermistor. The thermistor is buried in the soil and acts as a thermostat to control the increase in the temperature of the soil. Describe how an increase in the temperature of the soil affects the thermistor. So here's our command words here. Describe. They're not asking you to explain. They're asking you to describe how increasing one variable affects this device. Now, a thermistor is a resistor which changes its resistance according to the temperature. As we saw before, an increase in the temperature, so increasing temperature, this causes, now you can use this symbol here, which is a kind of symbol from mathematical logic. It kind of means implies, but you can use it like this. Examiners will know what you mean. So increasing temperature causes a change in the resistance of the thermistor. Now you can simply say a change in resistance, but in this case you can be even more specific. Again, going back to what I showed you before, increasing the temperature causes a decrease in the resistance of the thermistor. So 1 mark for this, 1 mark for that, total of 11 marks. Okay, so another question which many of you found particularly challenging was question 2. So let's have a look at question 2. So this was the, I believe, the second highest voted question which you all asked for, particularly those of you who voted for this. I see that some, actually I see some of you are also asking, does P is equal to I squared R work for the previous question? Well, again, going back to what I was saying about how to approach these questions, the first thing you should be doing before you actually start to answer a question is read through the values that you're being given. In a calculation question, it's very important that you either highlight or underline or make a mental note of, or even write down next to the answer area for yourself, what values are you being given so that you can more clearly visualize which equations actually apply. So many of you are saying, yes, you are right. P is also equal to I squared times R. This is another one of those equations which you do need to know about, and it does appear in the notes which I'm going to be giving you. So if we go back to the section on power of electrical devices, yeah, so you see here that, yes, another equation that you need to know about that specifically applies to electrical circuits is this one here. The power of an electrical device is equal to the current squared times the resistance. However, the reason I didn't bring that equation up is because if you're following the method that I'm advocating here, let's say you're not highlighting or underlining. Let's say you read through this and you make a list of all of the quantities that you're being given in the question. So right away, we've got V. V is equal to 230 volts. We're being given current, so I is equal to 11 amps. You're being given the time. Time we calculated was 7,200 seconds. But are you being given resistance? You're not, yeah? So if you see these, you should immediately be thinking, well, I know P is equal to V times I, because power also is going to be the equation that we need. We also know that we're looking for Q, we're looking for charge. So what we need is, or in this question as well, we need energy transferred, we need work done. So when you see this list and resistance doesn't appear in it, you can rule out the equation that requires you to know the resistance. Does that answer your questions? Because I see that several of you have asked in that previous question whether we should use P is equal to I squared times R. So by following this kind of method, this kind of systematic approach to picking apart what the examiner is giving you, what the examiner is asking from you, you're avoiding tying yourself up by, and also wasting time in an exam by trying to use an equation like this and then hitting a dead end when you realize that You don't actually have one of the values. Now, you could calculate the resistance. You've got Ohm's law after all. You've got V is equal to I times R. But that would be an additional step to calculate the resistance. Then you'd need to plug it into this. Yeah, it's a far more elegant way of solving it if you just go about doing it like this. Yeah, so you could solve it by P is equal to I squared R, but it's a kind of additional step. So ideally what you're aiming for is that you're trying to limit the time that you're spending. You're trying to limit the number of steps required for a solution. And in an exam, that's incredibly important, not just in terms of not wasting time. It's also important because the more steps you take to answer a question or a calculation, potentially the more points you can go wrong at. Basically, it's kind of like thinking about a machine with 50 moving parts versus a machine with 3 moving parts. The machine with 50 moving parts is more likely to go wrong because there are more things that can go wrong with it. Yeah. Okay, great. So let's move on to question number 2. So question number 2 is another one of these questions that many of you said that you struggled on. So figure 1 shows a graph of current against potential difference. This is, again, here we've got a I versus V graph. And this is for a solar cell. And they're telling you something about it. When light of intensity 450 watts per meter squared is incident on it. Now, this is an example of an exam question where an examiner is going to give you perhaps a unit or a quantity that you yourself are not familiar with. But if you really pause to consider it, if you really look at the stem of the question and visualize what's going on, you should be able to come to the correct answer regardless. Yeah. So let's have a look at what we're being told here. Watts is the standard unit of power. Yeah. Power is measured in joules per second or watts. Per meter squared. Well, meter squared is a measure of area. So when you buy a solar cell, what you're buying is a sheet of material which is producing or transferring a certain amount of energy from light energy into electrical energy. So again, have a look at the general definition of power here. Power is the energy transferred per unit of time. Energy transferred is going to be measured in joules. Time is going to be measured in seconds. And so power is going to be measured in joules per second, which is equivalent to the unit watts. So 1 watt is 1 joule per second, 1 joule of energy transferred from one form into another per second. But you're buying a solar cell where the light of intensity 450 watts per meter squared is incident on it. So think about what that means in terms of what we've said. 450 joules per second, watts, per meter squared of light energy is falling on that solar panel. That's what this sentence means. So even if you've never encountered this measure of light intensity, you can still pick it apart. You can still pause, really try and look at what the units are saying. And this is one of the other reasons why you really must not just memorize the equations, but memorize the standard units and what they mean. Watts means energy transferred per second. So every meter squared of this solar cell has 450 joules of light energy falling on it every second. That's what this means. So determine the power output of the solar cell when the potential difference is 0.5 volts and use the data from figure 1. Now this is a really tricky question because it requires you to really think about what's being asked here. So let's think about this. So let's start by looking at the information that we've been given. Determine the power output of the solar cell when the potential difference is 0.5 volts. Now you're being given a graph, right? So a graph will always relate one variable to another variable. So we have the potential difference in volts on the horizontal axis. We have the current in amps on the vertical axis. We're being asked, determine the power output. Power output is P measured in watts, joules per second. The potential difference we're being told is 0.5 volts, which is here. Now this should, on this graph, correspond to a certain amount of current. So you need to be able to read a graph, basically. So let's have a look at this graph then. We have increments of 0.1 amp going from one faint line here, 5 small squares equals 0.1 amp. So if 5 small squares equals 0.1 amp, you need to divide 0.1 by 5 to work out how much each one of those little squares is worth. So again, I'm belaboring the point here, but I really want to physically show you what you should be doing in an exam. If you're not comfortable with the question, you can still work it out. In order to read what this value is, it's kind of halfway across one of these small squares above the 0.9 amp level. So we need to know what each one of these small squares is actually worth. So we do this. 0.1 is 5 small squares. So each small square is going to be worth 0.1 divided by 5, which is of course 0.02. So this is 0.9. This small square above the 0.9 is 0.02, and so this is going to be 0.91, this value here. So we need to read off the graph correctly in order to work out, first of all, what the current is at this potential difference. So again, I'm kind of belaboring the point here, but you see what I'm saying here. So you read off the graph. Let me just go back here. So we're reading from here. So we follow this line up and we find that it intersects this line here, and it's a straight line which comes here. So if this is 0.92, this will be 0.91. So this value here is 0.91 amps. So we now know voltage is 0.5 volts. We've read from the graph, current is 0.91 amps. Excuse me. So determine the power output. Now, what equation do we know that relates power to voltage and current? Well, it's very easy. Power is equal to voltage times current, right? So power then, show the examiner. We know the equation, power is equal to voltage times current. We have both of those values in their standard units. So we simply, underneath, we substitute those values, 0.5 multiplied by 0.91. We then type those into our calculator, and we get a power of 3.47. Let's just do it. So we have 0.5 times 0.91. Yeah, so we have 0.455 watts. So power equals 0.455 watts. Now, in this case, some of you, another thing that I see a lot of students doing, sometimes unnecessarily in exams, is to round up or round down their answers to certain numbers of significant figures. And they seem to be doing this randomly without really paying attention to the question. Another thing that you need to be very, very careful of in calculation questions, unless it tells you to round up or down to a specific number of significant figures or a specific number of decimal places, please do not do so. So the guideline here is always leave your answer, unless you're told to give it in a certain number of decimal places or a certain number of significant figures, always give your answer to the same number of significant figures as the maximum number of significant figures given in the question. So in the stem of the question, we have this quantity here. This is 3 significant figures, right? This value here is 1 significant figure. So this obviously is the largest number of significant figures given to you in the stem of the question. And so if you're not being told to give your answer to a certain number of decimal places or significant figures, and you get this 0.455, 3 significant figures, you don't round it up or down. So 0.455 watts is where we leave it. So please always leave your answer to the maximum number of significant figures given in the question, unless you're told to round up or down to a particular number of decimal places or significant figures. Okay, so draw a sketch graph on figure 2. This is figure 2, right? to show how the power output of the solar cell varies with potential difference between 0.1 and 0.5. No values need to be included on the vertical axis. So you're being given the potential difference in volts, but they're asking you to sketch. There's that command word. When you're being asked to draw a sketch graph, all they're interested in is the shape of the graph. They're not interested in values particularly. They're just interested in how this variable affects this variable as this variable increases. They don't care about the units. They're specifically telling you do not need to put units on the vertical axis. Yeah. So how do we answer this question? Well, you're being asked to show how the power output changes between 0.1 and 0.5. Now, we just calculated at 0.5 volts, the power output is 0.455. So what we need to do is to get an idea of what the power output is between this point, 0.1 volts, and 0.5 volts. Well, if at 0.1 volts, so at this position here, if we look at the current, it's still 0.91 amps. Yeah. So if the current is 0.91 amps at 0.1 volts, then what do you think? What should we be writing here between 0.1 volts and 0.5 volts? What should we be writing here as the change in the power output? So this is almost a trick question. Many of you have said that it should be, many of you are still saying that it should be a line that looks like this, or a straight line. Obviously, I'm drawing it freehand. That's not the case, right? Now, the reason for that is very simple. Yes, at 0.1 volts, the current is still 0.91 amps, but the voltage is lower. It's 0.1 volts. So let's do a little quick calculation. So at 0.1 volts, current is equal to 0.91 amps. At 0.5 volts, the current was 0.91 amps. However, what does this mean about the power? So we calculated at 0.5 volts, the power was 0.455 watts. And we did that by multiplying the volts times the amps. If we do that at 0.1, the power will actually be less. It's going to be 0.1 times 0.91. So in this case, the power is going to be 0.091 watts. It's much lower than at this point. Now, again, because power is equal to voltage times current, if the current remains the same and the voltage increases, then power will increase in linear proportion. So in fact, it should be a straight line that looks like this, going through the origin. Yeah. So I think that one tripped up quite a few of you, unfortunately. Okay, so let's just finish off this last part C before we go into the Q&A section here. I know we're going slightly over the half hour, but it seems like we're almost finished. So the maximum power output of this solar cell is 0.52 watts. When the light intensity is 450 watts per meter squared, the cell has an efficiency of 0.15 at the maximum power output. Calculate the area of the solar cell. Now this, I think, was the question that tripped up almost everyone. I got emails about this and I got all kinds of suggestions. Many of you did actually get this right. Some of you even emailed me with the completed document, which is great. So let's work through this for the benefit of those of you who struggled with this question. So again, this is a tricky question. This is about as tricky as questions are ever likely to get in your GCSE Physics exams. You're probably not going to get anything more tricky than this, in this topic at least. But if you can at least understand the explanation for this, you're in good shape. So let's have a look at how we do this. So now, what we're being told here is that the cell has an efficiency of 0.15. Now, efficiency is, again, one of those general concepts that you will come across in physics. So there's a general term for efficiency. Whenever energy is being transferred, whenever work is being done by a device, it can either do so efficiently or inefficiently. Efficiency, so here, I think my graphics tablet is deciding to go a bit messy again, so apologies. Let me just fix that. So, oh, still not working. Might have to switch this on. Sorry, guys. The joys of live broadcasting. Let's see if this works. Okay. Come on. All right, let me just try that again. If not, I'll just do it over here. Okay. All right, great. So efficiency is another one of those equations that you need to know the general definition. Now, efficiency can be given as a decimal or as a percentage. Now, in this case, it's being given as a decimal. Efficiency, energy efficiency, is always the useful output, and that can be in terms of joules or power, divided by the total input. And again, if that's in joules, this also needs to be in joules. If that's in power, in watts, this also needs to be in watts. So this is a general concept. If you want to turn it into a percentage, you can multiply that by 100%, but in this case, it's not necessary because we're being given it as a decimal. So when the light intensity is 450 watts per meter squared, the light falling on it is at this intensity. The cell has an efficiency of 0.15 at the maximum power output. So we've just been told in the question, the maximum power output is 0.52 watts. So we're calculating at this maximum power output. So we'll write here, power is 0.52 watts, where if our efficiency is 0.15. So what this is saying is that we have a device, a solar panel, solar energy, light energy is going in. This is the total energy input. The useful energy output is electricity, electrical energy. So this is the useful output. There's going to be non-useful outputs. So heat, for example, is wasted energy. But energy is conserved. The total amount going in must be equal to the total amount coming out. But in this case, what we're doing is to calculate efficiency, we're dividing the useful energy output by the total energy input. So when we divide the useful output by the total input, we get 0.15. That's what efficiency means. So we can say that. So when the light intensity is 450 watts per meter squared, the cell has an efficiency of 0.15 at the maximum power output. So if the electrical power output divided by the total input is this, and the maximum power output is 0.52, then we know that the electrical output, so the total output of useful electrical energy is 0.52 watts. This is 0.52 joules per second output. That's this one. But the total energy input is unknown. Or rather, the total energy input is 450 watts per meter squared. So let's imagine that the total output is 0.52 watts. So we can rearrange this equation now, or rather just substitute values into this equation. Show the examiner the equation. So we have efficiency equals useful output divided by total input. So this efficiency value is 0.15. The total output, or the useful output, is 0.52 watts, but the total input energy is unknown. So let's just call this P subscript I, P, power input. But the input power is solar energy, isn't it? Yeah. And for every meter squared, we're getting a total input of light energy of 450 watts. So let's rearrange this equation for P sub I. So we multiply both sides by P sub I and then divide by 0.15. We get P sub I is equal to 0.52 divided by 0.15. And so we know that the total total input power for this particular solar panel, when we evaluate this, is going to be 3.47 watts. Yeah, but the total input power for every meter squared is 450 watts. We're trying to find out the area of the cell. It's watts per meter squared. Look at the units here. So input power is 450 watts per meter squared. Yeah. So if we want to find out what the actual area of the panel is, if the panel is giving out 3.47 watts and for every meter squared you get 450 watts, therefore the area in meters squared is going to be equal to 3.47 divided by 450. And so this gives us an area in meters squared of 7.7 times 10 to the power minus 3. You don't have to give the answer in standard units, but if you do it as a decimal, let me just show you here on the calculator. So we have 3.47 divided by 450. So this is 7.71 times 10 to the power minus 3. And so you can give your answer as 7.7 times 10 to the power minus 3. Okay, so I hope that answers your question. Again, this seems to be the one that most of you struggled with the most in this series of exam questions. Again, I will upload the mark scheme for this entire exam question packs for you to the private webinar resources page. Okay, guys, so that does it for that extra half hour or so, or slightly more than half hour now. Let's quickly go through the Q&A. So there's a lot of questions here. I'm going to go through the ones that have got the most votes here. So a lot of you are asking about the static electricity part. You're asking, let me see some of the other questions here. Yeah, so a lot of you were asking about the balloon and the electrons and also the insulators. The question seems to be if insulating materials are insulating because they do not allow electric currents to flow through them, how can electrons move through the balloon, or how can electrons oops, oh, little spike in CPU usage, interesting. Oh well. How can electrons move through insulating materials? Well, it's not that they move through them, it's charging by friction. It's the idea that friction between two surfaces of two different insulating materials will cause electrons to be transferred from the atoms of one to the atoms of another. Now, this is not the same as electrons moving through a particular insulating material. Or a non-insulating material, a conductor like a metal. Electrons can move through metals. That's what makes them conductors. But electrons can also be removed from metals in the same way that electrons can be removed from insulating materials. So I think it's just the distinction between electrons moving through a material in the case of a conductor versus electrons being stripped off an insulator by another insulator due to friction between those two insulating materials. I think that's where some of you are kind of getting a bit confused there. Another question that seems to be getting a lot of votes across all 4 Zoom rooms or versions of this question is asking about the light-dependent resistors and thermistors. So you're asking why does the resistance of a light-dependent resistor fall when it's when the incident light on the light-dependent resistor, the intensity of it increases. Some of you are also asking, along with that question, why is the resistance of a thermistor decreasing as the temperature rises? Now, I think in the case of the thermistor, many of you were asking that question because you're thinking about in a normal metallic or ohmic conductor. As the temperature rises, the particles, the atoms and the ions making up that material will vibrate more rapidly, and therefore electrons moving through that material in an electric current will collide with the ions more frequently, and this raises the resistance. And so why does the same thing not happen in a thermistor? Well, not without going into depth that goes beyond the GCSE specification, it's because thermistors and light-dependent resistors and other types of specialized resistors are made of semiconductor materials rather than metallic conductors, and these materials have slightly different electrical properties than the materials which make up for example, the wires in a circuit, or the resistors in a circuit, the variable resistors and fixed resistors in a circuit. Some of you were asking about, let's see what the next question here is. Yep, some of you were asking about the national grid. Okay, so let's quickly have a crack at that. So a lot of the questions about the national grid, or at least the ones that got the most votes, seem to be that you're asking about why does the national grid transmit power at high voltages but at low currents. So let's have a look at the section on the national grid. So again, feel free to browse through these. I will upload these to these slides to that page for you. But basically the reason is this. So let me just find yeah, so here we go. So the reason is this. It's to reduce losses of electrical power due to heating in these cables. Now, the pylons that connect these cables essentially stretch all the way across the country. So you're talking about hundreds and hundreds of miles of electrical cables. If you increase the current, then you're increasing the amount of electrons flowing per second through those cables, and therefore you're increasing the rate at which they collide with the ions, the metal ions in those cables, and therefore you are increasing the rate of heat dissipation through those cables. If, on the other hand, you increase the voltage, you can decrease the current while still maintaining the same power output. So let's have a look at why that works the way that it does, and it goes back to one of those equations that we talked about earlier. So let me bring up this slide here. Give ourselves a bit more space. So I mentioned to you before, one of the equations that we can use to calculate electrical power is this one here. P is equal to I squared times R, but P is also equal to V times I. So let's think about this logically. If you want to transfer lots and lots of power from one end of the country through all of this system of wires to the other, you can't change the resistance. I mean, to do so, you would need to either make the wires thicker, which is obviously not a good thing because the pylons would be less able to support their weight, or you can make the wires less long, which again is not an option because you can't make the country any shorter, or the distances that the electricity needs to travel from the power stations to the homes and the factories any shorter. So you can't really change the resistance. What you can do is change the voltage and the current. If you change the current, if you increase the current, you increase the rate at which those electrons collide with the metal ions in those conductors, and therefore you increase the rate at which heat is lost. If you increase the voltage but decrease the current, you're increasing the amount of energy pushing those electrons along. You're increasing the amount of potential difference from one end to the other, but that doesn't affect the rate at which the electrons are colliding with those wires. So if we increase the voltage but decrease the current, and the resistance stays the same, then what's happening, let me go back to those equations for a second, is this. What we're doing here is we are, okay, so power is what we want. We want to maximize the power. So if power is equal to voltage times current, and we can't change the resistance, then we can't use this equation. So here we could decrease the resistance. Theoretically, we could decrease the resistance while keeping the current the same, and while increasing the current and maximize the power that way. Rather, increase the resistance and increase the current, and we maximize the power that way. But you can't change the resistance. And even if you did, you would increase the heating in those cables. So this equation is not much use to us. What we can do is increase the voltage, but then that allows us to decrease the current. And again, it's the rate of flow of those electrons which leads to the rate of collisions, which leads to the energy lost from electrical energy carried by those electrons to heat in the surroundings. So for this reason, the national grid transmits power at very high voltages, but at very low currents. So what happens to the energy loss as heat as the voltage is increased? What do you think, guys? So A, B, or C? What happens to the energy lost as the voltage is increased, but the current is, let's just assume the current is kept the same and the resistance stays the same? Decreases, yeah. So the explanation to this is to reduce the energy lost as heat during the transmission of electricity. It's more efficient. Again, think of that term efficiency, the useful power output. The useful power output at the other end is electrical power. The wasted power output is the heating, the energy lost as heat. So it's more efficient to use a high voltage and a low current. Okay, so a couple more questions here. Well done, guys. So one of the questions is, what causes electrons to flow around a circuit? Okay, so this goes back to what, so again, that seems to be getting a lot of votes. Again, this goes back to the idea that a current is a flow of electrons, but nothing, even including electrons, will move unless you are pushing or pulling it. Things move because there are resultant forces acting on them. If you push an object and the resultant force is in a particular direction, the object will move or accelerate in that direction. If there is a resultant force in the opposite direction, it will move in the opposite direction. If the object already has momentum and there isn't zero resultant force acting on it, it will move at a constant speed in a particular direction. But in any case, to get that object moving from a standing start, you need a force, you need a push. And so electrons are objects. They are things that require forces to move them. But when forces move objects, they do work. Work is the energy transferred by something. So let's go back to this. Voltage is defined as the work done in moving a unit of charge, 1 coulomb. So if we imagine a charged object, let's go back to, in fact, let's go back to this. So let's imagine we have this charge here. Now, to move this charge from this point here to this point here, we need to exert a force on it. So let's imagine we get a positive charge over here, and the field lines join up this way, and the negative charge is moved towards this fixed positive charge in this direction because there's an attractive force on it. So in fact, let's use this point charge. Remember, the test charge is a positive charge. So there's a force acting on it because this positive is attracted to this negative because of the interaction between their electrostatic fields. So forces, when they move objects, they do work. Now, in the forces topic, when we go into the forces webinar later on in this sequence, we're going to go through this idea, but one of the equations actually applies here. When a force moves an object, the work done by a force, any force, an electrostatic force, a magnetic force, a gravitational force, the work done by a force moving an object through a displacement is given by the following equation. The work done is equal to force times displacement, S. S is the term used for displacement. So what this means is, if you have a charge, let's just call this charge Q, and you have a force acting on that charge, let's call the force F, and this force moves this object through this displacement from this position A to this position B. The work done by that force, the energy transferred to this object in moving it from point A to point B, is equal to the force times the displacement. Now this applies to electrons either in empty space or in any other situation, like electrons moving through a wire. In order to get them to move, there needs to be a force moving them. That force is provided by the power supply. The power supply sets up an electrostatic field between its two poles, essentially, that gives the electrons that electromotive force that moves them through the circuit. And so in this case, the work done is the force on the electron multiplied by the distance moved by the electron in the same line as that force. Now, because the work done is equal to the force times the distance moved, if we look at this equation, voltage is equal to the work done divided by the charge. Now, if we rearrange this equation to make W the subject, we get work done is equal to voltage times charge. So work done is also equal to the voltage between these 2 points. If we connect a voltmeter between these 2 points and measure the potential difference, The work done is equal to the voltage times the charge which moves between those 2 points. Now what this means is, if this is equal to work and this is equal to work, then this is equal to this. VQ is equal to force on the electron, on that charge, multiplied by the displacement, the motion, or the distance that charge moves along the same line as the force. And so this is literally what voltage is. Voltage, if we divide both sides by Q now, is the force on the charge times the distance moved by the charge per unit of charge. And this is the work done per unit of charge. So that's what a power supply does. It provides an electromotive force, a push, which pushes those electrons around the circuit. And by doing work on the electron, it is transferring energy to that electron. And that's the energy that gets carried around the circuit by those electrons, which then gets transferred into other forms in the other devices in the circuit. Okay guys, so it seems like we've hit the upper time limit for that. I'm sorry to have gone on for a bit longer than usual. I hope that was useful to you. If you have any questions, again, please do type those in the live chat on the private webinar resources page for this webinar on my website. You do need to be logged into the website, and you do need to have been one of the attendees for this. If you do, if you do try and go to this URL and you're not a member and you haven't booked a ticket for this, you're not one of the attendees, you simply will get an error message saying 404 not found. Please do send any private messages or type your messages into the public live chat here. It would be nice for you guys to actually be helping each other out with your revision as well. I will still answer your questions until after the exam period is over, and I will upload both the interactive video, the whiteboard notes and the slides as well to this area here. I'll also upload the mark schemes for this as well. Could you, if you could also do me a favor and maybe send me an email with a short review that I can use on my website, that would also be greatly appreciated, because then I can use that on the front page of my site to tell other people what they can expect as well. Okay guys, I hope that was useful. Thank you for attending, all approximately 500 of you. Thank you for attending, that was great, and I will see you in the next one. Take care.